This lesson is on section 4.5, isosceles and equilateral triangles. We start with the definition of isosceles triangles, which is a triangle that has at least two congruent sides. Usually we say if it has three congruent sides, we would call it equilateral, but as the definition states, it could technically be isosceles. The first thing we have to look at is the parts of an isosceles triangle. The vertex angle is the angle that sits in between the congruent sides. So our vertex angle in this case would be right here. The base is the side that is not one of the congruent ones. So this is the base. And the base angles are the angles that sit across from the congruent sides. So this is a base angle, and this is a base angle. The legs are the sides that are congruent. So this one and this one would be the legs of an isosceles triangle. We have what's called the isosceles triangle theorem, and it states that if a triangle is isosceles, then the base angles are congruent. So by definition, we know the legs are congruent, and then using the theorem, we say that the base angles are congruent. Those are the two most important parts of an isosceles triangle. An example of using the isosceles triangle theorem would be a problem like this. We know it's an isosceles triangle because the tick marks show us our legs are congruent, which means the angles that sit across from those legs are our base angles, and our base angles have to be congruent. So to solve this problem, we know that our vertex angle is 40 degrees, so our base angles have to make up the 180 degrees in the triangle. So we would take 180 minus our 40, and we would know that our base angles have to add up to 140 degrees. And since they have to be equal to each other, we would take 140 divided by 2, and each of our base angles would have to measure 70 degrees. In this section, we are introduced to something called a corollary. A corollary is a statement that goes along with a theorem. It's kind of the theorem's sidekick. Corollaries to the isosceles triangle theorem involve that if a triangle is equilateral, then it is also equiangular. So in other words, if all three sides are congruent, then all three angles would have to be congruent. What would the measures of those three angles have to be in a triangle? To figure that out, we would take 180 and we would divide it by 3, and each of the angles would have to be 60 degrees. The second corollary that we have that goes with the isosceles triangle theorem says that if a triangle is equiangular, then it's also equilateral. Those two are converses of each other, and they are both true statements. Examples of using the isosceles triangle theorem and its corollaries are as follows. The first example, I give you a triangle in which the exterior angle is 100 degrees. We can see that it's an isosceles triangle because of the tick marks. So we know that this angle is a base angle and that this angle is a base angle. So these two have to be the same measure. I can figure out what the measure of this one is because it's supplementary to the 100. If this one's 100, then this one has to be 80. And since it's an isosceles triangle, then this one also has to be 80. So this one is 80 and this one is 80. That gives us 160 degrees. So that leaves how many degrees for x? 180 minus 160 is 20. X has to be 20 degrees. Another example is using other polygons besides triangles. In this case, we have a pentagon. It's a regular pentagon, which means that all the sides are the same length and all the angles are the same measure. When I draw in the diagonals AD and AC, it splits the pentagon up into 3 triangles. Actually, 3 isosceles triangles. So I know that since this ABC is an isosceles triangle, that this angle and this angle will have to be the same. The question is, how can I figure out what those 2 angles are? And the answer is, because it's a regular polygon, we remember from chapter 3 that the interior angles of a polygon are figured out by taking the number of sides minus 2 and then taking that times 180. So the total of our interior angles is 540 degrees. And since it's regular, all of them have to be the same, so I would divide that by 5, and each one of our interior angles has to be 108 degrees. I'm only going to write them on these 2, but it also holds true for this angle, and this angle. Once I know what the vertex angle is in my isosceles triangle, I can figure out what the other 2 angles have to be. All I have to do is take 180 minus 108, which gives me 72, and I know that my base angles have to add up to 72. And since they have to be equal, I divide that by 2, and this angle would be 36, and this angle would be 36. That would be the same on this side of the pentagon, so y is 36. The way I can figure out x is using the same concept. The interior angle has to add up to 108. So if I take 108 and I minus off my 236's, minus off my 72, 108 minus 72, and that gives me 36. So x has to be 36, and then I can figure out what the other ones are based on that, because this is an isosceles triangle, so 180 minus 36 and divide it by 2, or because these 2 angles have to add up to 108 because that's the interior angles, I would take 108 minus 36 and I would get 72 here and 72 here. Make sure that you look for the tick marks in pictures that show that segments are congruent, because that will give you a hint as to which triangles are isosceles. That concludes this lesson. The homework for the different classes are as follows.